the second lecture in communications for GATE for ECE students. In the previous lecture, lecture 1, we have discussed the overview of the syllabus for GATE for communications, and we have started with the introductory topics where we have discussed about the analog and digital signals and about the classification of modulation techniques. So, in this lecture, before we move further into the discussion, the reference textbooks for communications I have listed out. So, for competitive examinations, please remember that always prepare your subjects using standard textbooks. Please follow standard textbooks. We have excellent authors which have penned down wonderful textbooks for all subjects under ECE, for GATE, and for communications. These are few of the textbooks which I suggest. Apart from this, you can also follow your own books, whichever you feel comfortable. So, Modern Digital and Analog Communications with B.P. Murthy. B.P. Murthy is an excellent author. He also wrote the textbooks on signals and systems. So, signals and systems with communications, these two textbooks, will be a very good choice. And another excellent textbook is Principles of Communication Systems by Cobb and Schilling. Very beautifully explained concepts, to the point, both for analog and digital communications part, along with information theory and random processes as well. And we don't get satisfied with one or two textbooks, at least you have to prepare for 3 textbooks or even 4 for every subject when you are preparing for competitive examinations such as GATE. So another textbook is Communication Systems by Simon Higgins. This covers both analog and digital communication. Simon Higgins is another excellent author, very well known author in the field of communications. There is a separate textbook on digital communications by Simon Higgins. So completely about digital communication. If you want to refer to, you can also refer to the textbook. So apart from these textbooks, when you prepare the theory, at the end of this, every chapter you have exercise problems. So those exercise problems you should be able to solve. That is very important. So the first time you may not get the answer, second time you may not get the answer, but eventually third or fourth time when you try, you will get the answers. So you will be more confident. So please work hard, understand the concepts, watch the video lectures, and solve the exercise problems which are given at the end of these textbooks. And another interesting reference which I want to mention here is the Shams Outline series. So Shams Outline series, these textbooks, they are like guides, okay? And these books are penned by foreign authors. And for every subject in ECE, we have Shams Outline series. Interestingly, these textbooks, they contain very less theory, but a lot of solved problems, step by step, and also exercise problems. So, for analog and digital communications, we have a Shams Outline series. So, this also will be available in market, or if you are studying in your library, you can ask for Shams Outline series. So, every subject, you can solve as many problems as possible, okay, by using these Shams Outline series. So ultimately, everything narrows down to how well you understand the concepts and how well you apply those concepts to solving the problems that are asked in competitive examinations. Okay. So having said that, so let us move into our lecture. Now let me run this one. right? So for lecture 2, the second lecture in this series. So as I told you yesterday in the previous lecture, the digital communications is what we are going to begin with. So under digital communications, the first topic, pulse code modulation. Okay. So digital communications. Under this, pulse code modulation. In short, this is called PCM. So before we get into the discussion, let us first try to understand and think about why digital is more preferred compared to analog these days. Okay, so whatever application you take, everything is digital. Your digital data transmission, the internet, the TV transmissions, your telephone communications, everything is digital. So why? Okay, what is the advantage of the digital communications over analog transmissions? Right, if you can think over for a moment, normally most of you will answer that less noise in digital. Okay, that is correct. That's the correct answer. Digital signals are more immune to noise. Okay, so how we will see that in our discussions, we'll prove everything. But if you think about some interesting examples which we see in our daily life, why digital is preferred over analog. If you can think about, okay, so let me tell you some interesting examples. These are all you are aware of. Now, earlier we used to have these tape recorders and audio cassettes, right? So audio cassette is, it contains a reel, and whenever a new film is released, okay, so the audio cassettes used to be released, and A side 3 songs and B side 3 songs, 6 songs in one audio cassette. You put inside the tape recorder and then you play it. Okay. So that is analog storage, the magnetic tape. But now if I convert that into digital, what is happening? You see your small pen drive, 8 GB, 16 GB, 32 GB, pen drives, USB drives. You can store huge amount of data, right? So number of songs, you can store in a pen drive or on a hard disk, will be hundreds or thousands, right? So same is the case with the video. Earlier we used to have what is called the VCR, video cassette recorder, or a video cassette player, and there used to be like a rectangular cassette. Okay, one full movie is stored there. So you insert that in your VCR or VCP, and that plays for 3 hours. So that is how you used to watch, films on TV using a VCR or a VCP. That is the analog storage, that cassette. Now, if I convert this into digital, the pen drives or your hard disks, you can store many number of movies, okay, within that single storage system. So you compare that with number of cassettes, audio cassettes or video cassettes that are required to store all these movies. It fills the one complete room, right? But when it comes to the storage on a digital format, on a USB or the hard disk or a CD player, CDs, so we are able to store large amounts of data. Okay, so digital requires very less storage, okay, right, compared to analog. and also it is inexpensive. Okay, that is one of the interesting things that we normally observe. Okay, earlier we used to have analog reel cameras. Okay, some 36 photos we used to capture, right? And when that is over, you have to change the reel again. But now we have digital cameras. You insert the card and the memory card, and then you can click any number of pictures and capture any amount of video. And also you can delete. Okay, if you don't like whatever you have captured, you can delete it again. You can reshoot. But that's not possible with the analog storage like reels. Okay, if you click the picture, then that is done. You cannot erase that. Okay, so these are all interesting examples. Also, one more example is earlier we used to have analog TV transmission. Okay, now the TV transmission completely is digital. So in analog TV transmission, normally the cable operator, he puts a cable on top of your house, and in case you bought a new TV but you don't want to take a cable connection, what we can do is, yes, we can simply tap the wire and put a wire inside your house, and you can watch TV illegally. Okay, right? And there is no way of knowing that the signal has been tapped until the cable operator, he comes and checks your connection on top of your house. But now, when you have digital transmissions, they set top boxes, okay, for every house. And if you want the connection, you require a set-top box. And even though a cable runs on top of your house, you can simply cannot tap it because the TV transmission is digital and encrypted. And to decrypt that, okay, you require set-top box. So security, privacy, these are all various, wonderful examples, okay, where digital transmissions are the reason why they are preferred compared to analog transmissions. Okay, so like these examples are many. Okay, so you can think of more examples as you just watch your surroundings and doing your daily course. Okay, now having said that, let us come to the first technique, pulse code modulation. So this is a pulse digital modulation technique. In the previous lecture, the classification of modulation techniques, we have seen pulse modulation. We have pulse analog modulation and pulse digital modulation. Pulse digital modulation techniques, we have pulse code modulation, differential pulse code modulation, and delta modulation. So all these three techniques, their objective is the same, to convert analog signal into digital. So let us understand in simple terms what actually is a PCM. So pulse code modulation means transmission of the message signal in the form of coded binary pulses. Coded, coded binary pulses. So that is what is PCM. So binary pulse, it means plus 5 volts or a minus 5 volts. For simple examples, we can say plus 1, bit 1 you can represent as plus 5 volts, bit 0 as minus 5 volts. So it is a binary pulse, coded. Coded means you are converting an analog message signal into digital, ones and zeros, and then you are transmitting that digital data in the form of a binary pulse, an electrical signal. So that is what is called pulse code modulation. So transmission of message signal in the form of coded binary pulses. Okay. So how this is accomplished? Okay. So that's what we are going to see with a simple block diagram. Okay. So let me draw that. So the analog signal is first given to a block called sampler, then followed by a quantizer and an encoder. So output is digital signal. So these are the three steps in pulse code modulation: sample, quantize, and encode. Okay. And interestingly, you cannot just swap these two blocks. You first have quantization, then followed by sampling. Also can be done. Okay, right? So that we will see the discussion. Okay, when we move into the next lectures in the due course of time. So, the analog signal, right? So, very simply, we take a sine wave. So, how we describe the sine wave? This is a signal which is continuous in both time and amplitude. So, continuous time and continuous amplitude signal. Continuous time and continuous amplitude signal. Now, that is your analog signal. So, time is continuous, amplitudes are also continuous, means number of amplitude levels are infinite. Now, the first block is sample. You are passing this through a sample. So, what the sampler will do? Don't put the answer that will sample the signal. Okay. So, those type of answers will not be normally preferred by your interviews. So, what a sampler will do is it converts a continuous time signal into discrete time signal. Continuous time signal is converted into discrete time signal, but whatever amplitudes are still continuous. Okay, so that is what the discussion we have seen in the previous lecture 1. Okay, so analog discrete time signal, that is a sampled signal. Okay, so the output of sampler is a signal which is discrete in time, but whereas amplitudes are still continuous. So continuous amplitude signal. Continuous amplitude signal. Okay. Now, since the amplitudes are still continuous, the next step is using a quantizer. So this quantizer performs what is called quantization. So here, the continuous amplitudes in this signal are converted into discrete amplitudes. That means the number of amplitude levels which are infinite are now converted into finite number of amplitude levels. So that is function of quantizer. So each block will do just one function. Okay, right? So output of quantizer now. So time is discrete. For simplicity say, I just put it discrete time, and the main difference now comes here. The amplitudes are now converted into discrete. So it is discrete amplitude signal. So discrete time and discrete amplitude signal. So both time and amplitude are now discrete. Now next step what we do is we encode these discrete values to generate your data ones and zeros. So the data is generated, okay, ones and zeros, right? So this can be any sequence. I just put 1010. Now when you are transferring it as an electrical signal, right? So bit 1, say positive voltage plus 5 volts, bit 0 minus 5. Bit 1 plus 5, bit 0 minus 5. That's simplicity say. So now here we have an electrical representation of your data. Okay. So that is your digital signal. So data is nothing but information that is stored in digital form. Okay. That is what is called data. Simple terms. So information stored in digital form is what is called data. So we have converted this analog signal into data ones and zeros. Now to transmit that, we are using the electrical representation. So plus 5 volts for logic 1 and minus 5 volts for logic 0. So these are the 3 steps, okay, that are performed to convert the analog signal into digital signal in pulse code modulation. So each block we are going to see in detail. Okay. Next. Right. So sampler, and this one now, the sampling theorem. Okay. Very interesting discussion we are going to do now. Sampling theorem. So, what sampling theorem says? That's the question. What sampling theorem says? Okay. Right. You will be saying some conditions, f is greater than 2f and all that stuff. But I'm not asking you the conditions. What actually it says? What actually it says qualitatively? Okay, that's the question. Right. So let me answer. So sampling theorem, what actually it says is how many number of samples I have to take from a analog signal, so that at the receiver I am able to reconstruct my message signal without any distortion. So that is what sampling theorem says. How many number of samples I have to take? Okay. So for example, for this signal, okay, in one cycle, I have taken 3 positive samples and 3 negative samples. Okay, right? So now we transmit these sample amplitudes, okay, towards the receiver. So you can see the time is now discrete. So now these sample amplitudes, 1.1 volt, 2.3 volts, 1.7 volts, minus 2.1, minus 3.2, minus 2.2, something like that. Okay, those sample amplitudes at some regular intervals are transmitted to the receiver. Now what the receiver has to do, when it receives these sample voltages, it has to reconstruct back the original message signal. Okay, so from these sample amplitudes, the receiver is able to reconstruct back the original message signal. Okay, very good. So I got back my original message signal perfectly without any distortion. So in this simple example, the number of samples I have took for one cycle of this message signal is sufficient to reconstruct back the original message signal without any distortion. Now, if for example, it's a hypothetical case where I take sample something like this. I take 2 positive samples and 1 negative sample, and then I have transmitted these 3 samples towards the receiver over a channel. Now, is it possible to perfectly reconstruct your message signal from these 3 samples? Right. You cannot perfectly reconstruct. Your reconstructed signal will look something like that. Okay. So as you can see, this is distorted, right? So that's what the sampling theorem says. Okay. So how many number of samples I have to take from a input signal, a message signal, so that at the receiver I am able to reconstruct back those signals without any distortion. Okay. So having said that, now let us state the sampling theorem in a more technical way. So sampling theorem states that a low pass signal band limited to f10 Hz. So low pass signal band limited to f10 Hz